Hello, and in part 4 we're going to look at ferromagnetism and how to make effective inductors. Firstly, a quick revision of dielectrics and polarization. We've seen this slide before. It's just a reminder that for a dielectric insulator material here, if we put on an external electric field, we get this polarization field that appears in the opposite direction, caused by all the little dipoles produced by the application of this external electric field. The internal electric field, which is the one that's important when determining the properties of a capacitor using this dielectric, is then the result of the superposition of both of these electric fields. And since they're in opposite directions, the internal field is smaller than the external electric field. There are corresponding effects in magnetism as well. There are some comparatively small effects known as diamagnetism and paramagnetism, but the one that's going to be concerning us is one called ferromagnetism and a variant called ferrimagnetism. These effects are found in only certain types of materials, notably iron. Now, if you just have a lump of iron, then that lump of iron has inside it a whole load of small magnets called domains, and each one of these magnets will be aligned in a particular direction. And just a random lump of iron will have all of its domains aligned randomly so that all the magnetic fields will tend to cancel each other out. However, the direction of the magnetic fields in these domains is heavily influenced by the external magnetic field. Apply an external field and all of these magnetic fields, all of these little dipoles, will tend to line up in the direction of the external field. In ferromagnetic and ferrimagnetic materials, quantum effects lead to the magnetic fields in the domains tending to align in the same direction as the applied magnetic field. The net result is that the effect of these magnetic dipoles is to increase the magnetic field inside the material, so that the magnetic field inside is actually larger than the magnetic field outside the block of material. This is completely unlike the case of electric fields and dielectrics, where the field inside the material is smaller than the external field. Here, for a ferromagnet or ferromagnetic material, the field inside the material is actually larger than the external magnetic field. We have an effect which amplifies the magnetic field. In dielectric materials, we talk about the internal field and the external field in terms of the E field and the D field. The E field is the actual electric field inside the material, in the sense that that is the force on a unit charge. So this E field inside is the difference between the externally applied field, known as the D field, and the polarization field generated by all of the small dipoles inside the material. So we can write that the electric field inside the material is the externally applied electric field minus the polarization field, and for historical reasons there is a constant known as the permittivity of free space included in that formula. In the case of ferromagnetic materials, we have the externally applied magnetic field, that's the H field, adding to the magnetization field produced by all the small dipoles inside the ferromagnetic material. And again, for historical reasons, there's a constant of proportionality put in, known as the permeability of free space. And it's the sum of those two fields that generates the actual magnetic field inside the material, known as the B field. Now, in some cases, you can assume that the M field is proportional to the H field. We could write that M is equal to K times H, perhaps. And then we could write the magnetic field inside the material as mu naught times H plus KH, or just mu naught 1 plus k times h. And this constant here, 1 plus k, has a name as well. It's known as the relative permeability. And we can write the formula like this. The magnetic field inside the material is the permeability of free space times the relative permeability times the H field. And the H field is the magnetic field actually generated by the currents. Now, I should warn you that this assumption here, that the magnetization field is proportional to the H field, is not a terribly good assumption. Most real materials don't have a magnetization field which is exactly proportional to the externally applied magnetic field. However, I will leave the details and the consequences of that until a later talk. We can now go back to that expression that we had before for the magnetic field induced at the centre of a coil of wire, and note that this is the H field. The H field is the externally applied magnetic field, that's the one being caused by the current, as opposed to the B field, which is the magnetic field that actually exists within the core of the inductor. And if we look at that formula, we can see that to get a large H field in the centre of the coil, ideally we would like a large number of twists of the coil, N. We would like a large current to be flowing, that's the I, and we would like the distance r, that's the radius of the coil, to be small. The other thing that would give us a large B field, that's the magnetic field which is actually going to generate the EMF, is if we could find a material with a high relative permeability. And that suggests using a ferromagnetic or ferrimagnetic material for the core of our inductor. Now, you might think that since the magnetic field strength at the centre of the coil increases as the radius of the coil decreases, that we would want a small value of r, a small value for the radius of the coil as well. A full analysis of the situation, however, shows that this is not the case. It's not just the magnetic field in the centre of the coil that produces an EMF in the inductor, it's all of the magnetic field flowing through the coil. And a smaller radius results in a smaller area in which the magnetic field can be produced. In fact, to get a larger inductance, it's better to have a large value of radius so that the area of the coil is greater and a greater total magnetic field can be generated. And you can buy these things. Here are some sample inductors. This one only has 2 twists of wire around a ferrimagnetic core. This one has 5, this one has lots. What's inside this one is just a large number of twists of wire around a core like this, encased in a plastic case. They're not easy components to work with because a real inductor doesn't behave very much like an ideal inductor. One problem is that because you want to have so many twists of wire for a large inductance, that requires a lot of wire, a long length of wire. And if you're going to have a small package, then the wire has to be very, very thin. And with a large length of very thin wire, you will have an appreciable resistance. Another problem with inductors is this assumption, that the magnetization field is proportional to the H field, which for a lot of materials isn't true, or at least it isn't very accurate. These effects make inductors quite difficult to design accurate circuits with. So if you need some kind of time-dependent component in your circuit, it's usually much easier to design with a capacitor than it is with an inductor. I can't resist adding this one in again because it's such a common error that people make when they first start working with inductors. Immediately after the switch closes, what would the voltmeter read? And the answer is 1 volt. Because before the switch is closed, there is no current flowing, and you cannot change the current through an inductor instantly, because that would imply an infinite voltage was being generated as a back EMF. So if you cannot change the current instantly, and the current was 0 just before the switch was closed, then the current must be 0 just after the switch is closed. If there's no current through the inductor, there will be no current through the resistor. If there's no current through the resistor, there will be no voltage drop across the resistor, which means that this point here would be at 0 volts, just at ground. But this point here would be at 1 volt, because we've just closed the switch and attached it to this voltage source. So we have 1 volt here, 0 volts here. The voltage across the inductor would be 1 volt. The voltage across the inductor has suddenly changed from 0 to 1 volt, but the current through the inductor hasn't. It's still 0. That's all for now. In the final one of these talks, we're going to have a very quick look at transformers.